This isn't homework. This is actually on the other side of the homework. So this one I did make a video for, but on the other side, some classes we didn't get all the way through this in-class example. Other kids had to leave early, and in one class, I had to leave early. So I'd like to just reconfirm that this makes sense and that we know what we're doing here. So these worksheets are having us decide, can we classify this shape? So if we go for 3 and 2, -1, we get a shape. And when we spoke in class, some students thought maybe this is a rhombus. It definitely doesn't look like a square. Maybe it's a parallelogram. That was probably the most popular. And so our hypothesis were these two things, and now it's time to prove it. So if I really do think this is a parallelogram, to prove it, I would have to prove that it meets the definition. So the definition of parallelogram is opposite sides are parallel. So that's where I'm going to start. You can start in any point in this, but if we start in a hypothesis where we think it's a parallelogram, then to help me out, I would find the slope of the side. So the slope of side MN appears to be going up. So I'm going to put rise over run. Now, as I look here, I went up 4/2. So the slope of this line must be 2. And for some, it's helpful if I leave it like that because they can notice a pattern later. So I'm going to go ahead and do that. Now, if this really is a parallelogram, then this side would be the same slope. So I'm going to test out the slope of PO. So as I read the points left to right, I say to myself, oh, it's going uphill again. So I'm rising and then I'm running. I rise 1, 2, 3, 4. I run 2. So up, that is same slope. So the terminology of parallel is a relationship that we find that parallel lines happen to have the same slope, and we've confirmed that. But parallelograms have to have 2 sets, so I'm going to have to continue my journey in investigating a little further. If I continue to find the slope of NO, I notice this one is also going uphill. It looks like it goes up 1, 1, 2, 3, 4, 5, 6, up 1 over 6. So rising 1, running 6, so that's my slope, 1/6. Now I want to compare it to the opposite side, so that would be the slope MP. I also notice is going uphill, so if I go from point M to point P using the grid lines, I'll go up 1, 1, 2, 3, 4, 5, 6. Interesting, right? So these have the same slope as well. And you know what we've done? We've proven it's a parallelogram. But if we see in class, rhombuses are also parallelograms. So we kind of have to go about disproving that it's a rhombus. So rhombuses have 4 equal sides. So we pretty much set the stage to also then find the length. Let's go ahead and do that. So if we find a length of a side, I have MN. Again, if I think about this imaginary right triangle, I went up 4/2. This triangle, 4, 2, is in fact a right triangle. And using Pythagorean theorem, I can solve for that hypotenuse. And that is the length I'm looking for. So I get the numbers 16 plus 4, or also known as the square root of 20. Now I notice over here, and also inside my equation, I went up 4/2. So it's the same exact picture. So in essence, I've reconfirmed that the length of MN does have to equal the length of PO, and those are both equal to the square root of 20. Because in both instances, I went up 4/2. Okay, now let's see if we can reconfirm that these opposite sides are congruent. So if I remember back, I went up 1/6, up 1/6. You could be picturing a right triangle that looks like that, 1 and 6. And so this hypotenuse would be the square root of 1 squared plus 6 squared, otherwise known as the square root of 37. Now, once again, you recollect that both times we went up 1 over 6. So both times you would have drawn an imaginary right triangle. So both times we're reconfirming that NO, the length that is, and the length of MP both need to be the square root of 37. Now, I'm hoping you're thinking in for there a second. This thing is not a rhombus. If it were, it would be square root of 20, square root of 20, square root of 20, square root of 20, or square root of 37 all the way around. Square root of 37, square root of 37, square root of 37, square root of 37. Nope, that's not what we have. So, it's definitely got to be a parallelogram. I don't know what else it could be because of that. But there could be a couple other weird things maybe. Like if the diagonals met in at 90, that would confuse me. I don't think it can because that's reserved for rhombuses. Maybe this thing would be a kite, but no, that's not going to work. Kites have consecutive sides that are equal. And this side is this square root of 20, and that side's the square root of 37. So notice consecutive sides are not equal. So I do feel like it might be a really good time at this point to go ahead and calculate the perimeter because I know the length of every side. Now, if you don't have a calculator at home, it's not a big deal. In fact, it's a good practice for the end of course exam because half of the test is no calculator. So if I didn't have a calculator, I'd probably leave the answer like this because I have 2 square roots of 37 and I have 2 square roots of 20, and that's my perimeter. Okay, so now I think the real tough question here is trying to figure out the area, and I'd like to do that now. And so the problem though is notice I don't have any right angles. So I really probably should move forward and find the slope of the diagonals because if they were in fact 90, then it would help me have an altitude. Right now I don't have an altitude. Notice these are not opposite reciprocals. That would be like a -1/2 or a positive or a -6. I don't have opposites at all. Both of them are positive. Okay, so let's look at these diagonals. When I cross these diagonals, I notice that I get the point, the middle, and I can't call it M, so I'll just call it J. Point J looks to be at 0, 1/2. Now I can reconfirm that with this midpoint formula. So the diagonal MO would be the midpoint of the 2 coordinates M and O, 4, 3, right? So when we see this, we say to ourselves, okay, I add the 2 x coordinates and divide by 2. I add the 2 y coordinates and divide by 2. Good stuff. I ended up getting what I had hypothesized. Now I can reconfirm if MO has that endpoint, so should NP. So the diagonal of NP is the middle of the coordinate -2, 2, and the middle of coordinate 2, -1. So taking a second look here, I'm expecting the same thing. That should be a 2, right? Add the 2 numbers, cut it in half. Add the 2 numbers, cut it in half. Once again, I get this coordinate 0, 1/2. That's point J. So I've double, triple checked. Now let's look at this slope. So if I think here, this one MO, the slope of MO is going uphill. So let's count it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So I rose 5, I ran 8. So I can calculate pretty quickly the length of that. That'd be 5 and that'd be 8. So the length of my diagonal, MO, would be the square root of 5 squared plus 8 squared, and I need to remember to take the square root. Okay, so the square root of 89. Interesting. Okay, now I'm going to find the slope of NP. So the slope of NP would be falling. Okay, so when I go from N to P, I go 1, 2, 3, 1, 2, 3, 4. So I fell 3, I ran 4. Notice these aren't opposite reciprocals. So just as we had hypothesized, those are not 90-degree angles. So we do need a different strategy. Let's go ahead though and find the length as they've asked. So I fell 3 and I ran 4. So I hope you're recognizing that's a pretty popular triangle right there. I'm going to get the square root of 9 plus 16, which is the square root of 25. So the length is 5 of that diagonal. Okay. So the one and only thing I haven't done is find the area, and I have no right angles to do it, none. Now we can approximate and just count the boxes, but one technique we learned a long time ago, it's been all the way back in September, is to make a big box around it and then just cut off the pieces we don't want. I think this is a really terrific strategy. Not the only strategy, but a really good one. So let's do it. I notice right off the bat that the whole area here, so I know my shape, which I know now is a parallelogram, can't be any bigger than 5 by 8. So the whole area is 5 by 8, also known as 40 square inches. And you can count those boxes, 5, 10, 15, 20, 25, 30, 35, 40. There they are. But our shape's smaller than that. So I'm gonna cut a few things off. I noticed that these 2 boxes here can totally be cut out, and this box, those 2 boxes down there can totally be cut off. So I'm gonna do that. Minus 1, 2, 3, 4. Minus 4 square boxes. Okay. Now, I should also be thinking to myself, you know what, this sounds familiar, because some information I collected before I can use here. Here's a right triangle, and I'd like to cut that part off. And I actually already know its dimensions. It's a 2 by 4. So off to the side, I could draw a triangle that's 2 by 4. I have another one exactly like it that I'm gonna just nest in like that. So that's going to be really helpful here in a minute. It's kind of a cool strategy. So notice I want to cut off this triangle and this triangle. So essentially I want to cut off that whole rectangle. And I actually know the area of this that I want to cut off. It's just 4 times 2, which is 8. So when I think up here, I want to cut off this rectangle, bye-bye, and that rectangle, and that's a total of 8. I want to cut off those 4 squares. Those are gone. Bye. And so I'm left with these 2 triangles. This one I know is 1 by 6. And this one up here I know is also 1 by 6. So when I think about this, the last little piece I need to cut off is 1 unit high and 6 units long. So the area of that, 1 times 6, is 6. Now here we go. We're just about ready to finish it out. So the area of our parallelogram would be 40, take away 4, take away 8, take away 6. And that gives me the area of 22 units squared. If it makes you feel better, you can write it down here in the place where we talked. And I'm gonna have that little square, okay? Thanks for joining me. Enjoy the weekend.